Yes.
And it will give you a shuffled version.
Yes.
Which is the D series for that particular I. That is
Okay.
the SD. Okay. Now while you do the shuffling, what is happening is you're computing the element to set function.
Minimizing.
You're doing this, yeah, with respect to another set function. There's an element to set function. So the set function with which you're trying to minimize and choose the next element is these sets. So these are the different SKs.
Okay, so the SK bar, that's one set that you're using to do the computation. That's different than the SD of I.
Absolutely, yeah.
It's different.
It's completely different.
Okay, and here you're saying you're given this shuffling SD of I in a guided way. You're given SK bar. Now you take any subset of F such that there's
at least one element that is in the D series that is not. Well, you have one element that is in the set you take that is not to the D series.
Okay, so xk plus 1 has to be in x hat, in s hat.
Yes. Yes.
Is that there?
Yes, and it should not be in SK.
Okay, it's not an SK and it's not an SD of I, or
Yes. It is not in SD of I and it is in S hat. Even one element.
okay,
So
and then
basically
you automatically
you're
get
messing
that.
up the SK hat. Anything that's the SK hats are the golden pieces. Those are the golden eggs. Those are the optima.
Yes.
One of the optimas in there. So if you have even one element that is corrupting the optima, then you would not get the global maximum. You would have this
Okay.
problem. This will be less.
Okay.
Okay. That's the reason we are starting from the power set. We are reducing the search space to just the starting sets, which are less.
Okay, so
And
kind
you-
of the upshot of this is if you're doing some kind of search algorithm,
Yeah.
then it says, oh, you only have to check something much smaller, so presumably you get a much better runtime for some
Yeah, a
algorithm.
lot smaller because the power set really explodes very quickly.
Yes.
So, if this was like a statistics problem, you had a lot of variables. These days in genomics, you could have millions of variables. There's no way you can search 2 power million. I don't know. Well, that could be a strong statement, but I could not search on the laptop doing that, but this I could do. At least in the order of n cube kind of algorithm. So this algorithm is going to be order of n cube times g, where g is the time required to do every evaluation of d. So that's where complexity is going to be. I'm not a complexity guy myself. The most important thing, I should have called that. So this is joint work done with Yulia Kempner, my co-author. Okay, I should do a tribute here. Okay, great, wonderful co-author. She's got a lot of experience in discrete math. I've had to use that guy, but we were able to do this cross-fertilization. Okay, so this is an algorithm. So I'll slowly move and glide towards the statistical side of shots, but that's just one. So let me state the algorithm. English with very little symbols. Step 1. Generate all D series for all I. Okay. Step 2. Generate a D cluster for each D series in step 1. Okay? We generate the D cluster. Now 3, evaluate MD of D clusters for all D clusters. And choose all maximum D clusters. You return this. Those would optimize that global, right? Okay, now statistical side of things. Okay, so there's an interesting function called a distance covariance in statistics. A normalized version of it is called distance correlation. It's an analogous idea to Pearson's correlation or Spearman's correlation. So the thing is, Pearson's correlation measures only linear dependence. So you're looking at linear dependence between random variables, whether it's +1 or -1, or independence if it's close to 0. Now, distance correlation is a more full spectrum version of that. Clearly, if distance correlation is 1, these two random variables are statistically dependent, for sure. And if it's 0, they are statistically independent variables. Nonlinear correlations, whatever be the dependency, this is proper statistical dependency. So, how is distance covariance measured? So what we prove is a quick overview of the direction again. We prove that the distance covariance is a quasi-concave set function, which is the first thing that I started with. And then we also come up with monotone linkage functions of distance correlation, of distance covariance. And we pose that problem in order to find subsets of random variables that are diverse, and by diverse I literally mean are statistically as independent as possible. So instead of clustering, which is grouping things with respect to dependency, here we are basically finding subsets that are as diverse as possible. So how do we do that? I make this D as my distance covariance. I put a negative in it. So what we're looking for then is the other end of and the good thing about distance covariance is it's always between 0 and 1, so it's not between -1 and 1 like Pearson's correlation. So that just flips the coin, since it's monotonic properties to it. And then it starts looking for the subset that will be more diverse. That's the overall upshot of the findings. Now, these are some of the statistical side of the proofs, but let me define distance covariance. Mu square of random. These are no longer the exact subsets I'm talking of, but I'm talking of subsets of random variables. So any x and y I'm using here is a random variable. Is defined as, so this is the population version of it. There's going to be a sample statistic that you can compute from data. The population version is integral, let's assume x could be RD, well, RP, and y could be RQ. This is another vast improvement or use over advantage over Pearson's correlation, because Pearson's correlation needs the inputs to be of the same dimension. But here you can have a random variable in RD space, RP space, and another in RQ space, P, not necessarily Q. Is defined as integral D plus.
Quick question, you say random variables in there, you mean it takes values there? Because I think of it, random variable as a measurable function.
Yeah, so this is the population notion of it. I'm talking of a random variable as a measurable function here. That's why I got the
defined on
but
p-dimensional real space.
Yes, yes. So as is very popular, every population version of a statistic has a sample statistic, and you have some sort of a convergence loss on as n goes to infinity. How well does the sample statistic estimate? It's just like population mean versus sample mean.
N means sample size?
Yeah. Yes. So integral, we're looking at characteristic functions, phi joint characteristic function, phi x, y, minus the marginal characteristic functions, phi x of t, phi y of t. This is a norm over functions. So we're looking at, this is the probability law. If you had a statistically independent variables, if x is independent of y, your joint characteristic function can be written as a product of its marginals. But if they're not independent, you're measuring how far they are from independence. And that's why, as this becomes more and more, you know that they're more and more dependent on each other. And you can always have a normalized version of it. There's an integral, there's a really complicated weight function that gives you all the properties. But that's not the purpose of the talk, so I'll skip what the weight function is. It's a really messy function. Okay, so this is what we have, and now what I do is I'll show you the overall statements that we proved in our paper. Our paper, you can just search combinatorics of distance covariance, and there's a linear version. subtitle to it. I should have put it shorter, but it is what it is again. But it's an archive, so I can probably put a subnote. All right, so this is the first thing that we prove. We prove that the negative distance covariance S intersection T, comma Y, is greater than or equal to the minimum negative distance covariance of S comma Y, comma, let's not do that, comma, negative distance covariance of T comma Y. So we're looking at, remember these are pairwise functions now from where we started. So what I did is I fixed the Y back here for the first pass. The Y is fixed, this is Y. And then the combinatorics is being done with respect to the first argument. So this says it is a quasi-concave set function of this argument given a fixed Y. Usually this makes sense for applied purposes because in problems like regression or classification and statistics or machine learning, you always have a response variable, you have a bunch of input variables or predictors or covariates. You want to learn functions that go from the input to the output. Or you want to learn the subset of your columns of your data that are most dependent on your response variable. That's going to be a good data set for feature selection or a subset of variable selection. Or you can also find subsets that are most independent, because, or you can do a mix of both, because you don't want to select variables that are highly dependent but also highly correlated. That's a problem as well.
So was phi sub x was the...
This is the joint characteristic function.
Okay, so is that the one that's like the Fourier transform or the one that's like the Laplace transform?
Yeah, there's a Fourier transform relation between the characteristic function and the density, but the characteristic function is this. So for a given random variable x, we're looking at an expectation of e power I t x, where x is your random variable we were talking about. And
okay, because then if you
is
took derivatives, it would give you these correlation functions.
Yes, and since my x is a vector in RD, what happens in vector cases? You have t transpose. You have this in RP, but this is in RP. If you had a matrix, then random matrix, you have a trace in here. Okay, so that is what this is. So we prove this, and then we come up with some more results that I'll go over. So what I'm doing here is more of a quicker overview of our part of the application, apart from doing this stuff. So we do that, and then what we do is basically compute the follows. I define another, this is not the famous pi, I'm just using it as a name of a function. Pi of, so basically what we do is we do pi of xi s is equal to sigma for all sj belonging to s. So s is a set of random variables here. We do a sigma of negative distance covariance of xi comma sj. Okay. We do that, and we show that this is a monotone linkage function. So this is an element to set function from one random variable to a bunch of random variables. Now this could have been my y, for example. And this could be my input features in my statistical regression setting. We do that, and this is a monotone linkage function. We show that it is a monotone linkage function. And using that as our d, we solve for we solve this problem basically. And for that, we do that showing. And to prove that this is a quasi-concave set function, I'll spend a minute maybe on a very interesting inequality. There's a story to it. So basically, it was published in Analysis Statistics with regards to this inequality, and there was a small mistake. It was supposed to be less than or equal to 1, but the respective authors put in less than 1. And then that paper was heavily cited because distance covariance and concepts around it are very popular these days. And so he came up with a correction, kind of an addendum paper, which was about 2-3 pages, and that got heavily cited as well because the inequality proved to be very useful for other people. So it was like a 2-page correction with 50 or more citations. So the inequality is, which helped me prove, apart from doing my own stuff, to get to the quasi-concave set function thing as follows. There's no name for it, so I named it with the name of the author. So distance, covariance, inequality. Okay. So that nice gold mine, which is follows. It says the distance covariance of x plus z. This is a proper addition. This is not a set unit. Comma y is greater than distance covariance of x comma y if this is a proper greater than. If z is this is a symbol for independence, but it's actually it's not independent. So if z, random variable z, is not independent of x comma y, we have that. And it's an if and only if condition. So based on what this situation is, you can put this one, the greater than symbol. So what we did is the follows. We took 3 conditions. So as I conclude the proof for that, we take 3 conditions because we have S intersection T guy in here. What we do is we look at the case where S and T are intersecting like this. We look at the case where S is inside of T. And we look at the case where T is inside of S. Okay. And then we use the Kosovo, that inequality, and we plug it in here and see what happens. And after a series of steps, we get that in all 3 cases, which are all the possibilities, this, which is the quasi-concave set property, stands good. So that's how we did that. And then we did this whole showing process. I think I'll get a break there. And thank you. Thank you very much.